Now let's look at the second example. Okay, for the second example, a marble was dropped from the top of a 300-meter tall building. Okay, we have two questions here. So two RTFs are required to find, but let's take it one by one. Okay, so I'd like us to solve for letter A first. So we're gonna ignore B for now. Okay, we're only gonna solve for A. So whenever there are two RTFs in a problem, deal with them one RTF at a time. Okay, so a marble was dropped from the top of a 300-meter tall building. Okay, so this is a 300-meter height. Okay, and because we're actually recording displacement, and displacement is a vector quantity, remember that if the displacement is measured below the point of release, because this is where the marble starts, right? Okay, now, the 300-meter is measured below the starting position of the freely falling body. So if that displacement is measured below the starting point, you have to make it negative. So that's how it's going to look like. So that's one of the given right now. You have displacement equals negative 300-meter. And then once again, acceleration is negative 9.8 meters per second squared because it's still a freely falling body and it's still about Earth. It's still happening on Earth, rather. Okay, what else do we know? Initial velocity is obviously 0 meters per second simply because the object was dropped. And we know that the initial velocity of dropped objects is actually 0. Now, going forward, we have to identify the RTF. So the question is, how fast is the marble just before it hits the ground? So obviously, we're solving for final velocity. Okay. Well, you can put y for the subscripts, by the way. I actually missed it, but it's okay because we understand that we're dealing with vertical motion anyway. Okay. So now final velocity is the RTF. That's what we want to solve for. We're being asked for how fast is the marble at this point right before it strikes the ground, and that's final velocity. Okay, so the RTF is final velocity. The next question is, what is the missing variable? So once again, these are the variables that we have in kinematics: displacement, acceleration, time, initial velocity, and final velocity. Okay, now we have seen that D is given, A is given, initial velocity is given, and then the RTF is final velocity. Therefore, the missing variable is actually time. Okay? So what? Once again, we pick the working equation based on the missing variable. If the missing variable is time, we have to use equation 4 because equation 4 does not contain time, which is the missing variable. So let's go forward. So we're going to use equation 4 for this one. Okay? So that is Vf squared equals Vi squared plus 2AD. And then recall earlier that initial velocity is actually, where is it? Okay, there. You can see it here. There you go. Okay, initial velocity is 0. Okay, what does that mean? And this equation, we can cancel v sub I, including the exponent, of course. So we're going to have Vf squared equals 2AD. Okay, we're not yet done simplifying it because we're solving for v sub f, remember that. And there's an exponent too. Now, to get rid of that, you have to get the square root of both sides of the equation. And that gives us v sub f equals square root of 2ad. Now, just recall in math that whenever you want to cancel an exponent, let's say 2, just get the square root of that because the square root of vf squared is vf. So you'll actually get led to this one. Now, the next thing that we have to do is to plug in the given variables in our equation. So that would be Vf equals square root of 2 times negative 9.8 meters per second squared times negative 300 meters. Okay, and then let's use a calculator for us to solve for the final answer. So that's 2 times negative 9.8 times negative 300. That gives us 5,880, and the square root of that is 76.68. Okay, so 76.68 meters per second. So that's our final answer for part A. Okay, you can actually see that it's pretty fast. Like 30 meters per second is actually an overspeeding bar already in our context. So that's more than twice the speed of an overspeeding car. So just imagine if that marble falls on your head, for example. You can't imagine what might happen to you. So that's how fast a freely falling object can get. Although, actually, there's a point where it would reach a constant speed and it will stop accelerating. It has something to do with the concept of terminal velocity. If you want to know more about that, you can search about the concept of terminal velocity. But in this case, where we are assuming freely falling bodies, we're really going to assume that it's accelerating throughout the entire trip. So the final velocity can be as high as 76.68 meters per second. Now let's proceed to the next RTF, because there are two required to find in this particular problem. So at this point, I'd like us to ignore part A and then let's solve for part B. Okay? It says in the same problem, how much time did it take for the marble to reach the ground? So the same things would apply. The initial velocity is still 0 meters per second, acceleration negative 9.8 meters per second, and then the displacement is negative 300 meters because this is measured below the origin or the starting point of the marble. Okay, now this time the RTF is actually time, and obviously in this case the missing variable would be final velocity. Some student would ask, Miss Leia, how come we don't just use this as well? So that will be very versatile with our choice of equation. Why aren't we using v sub f as a given when in fact we have solved for it before? I strongly encourage you, I strongly discourage you to use a value that you only solved for. Because if you made a mistake in this calculation, then your second required to find will also be incorrect. So the safest way to do it is to disregard any variable that you have only solved for unless you don't really have a choice or unless you really have insufficient given variables. So in this case, let's ignore that v sub f is known because you only solved for it. So let's treat final velocity as a missing variable. And since final velocity is the missing variable, we're going to pick an equation that doesn't have the missing variable. And that is equation number 3 because you can see final velocity is not in this equation. So that's our equation of choice here. So that would be v along y equals v I t plus a t squared divided by 2. You can get rid of y as long as you're conscious that you are dealing with the y components. I'm not very strict with that. As long as you know what you're doing. Actually, you can also put y for acceleration, also for initial velocity. But again, it's not a big deal as long as you are very careful to plug in the right values that you are talking about vertical motion. Okay, so since we're solving for time, we need to isolate time in this equation. But before that, I'd like you to notice once again that v sub I is 0 meters per second, which means to say that you can cancel this in the equation. And you're going to have v sub y equals 80 squared divided by 2. Okay, now let's go to the next page of the frame. So at this point, we have v equals 80 squared over 2. And again, you can put y there if you want, if you're being OC. And then let's isolate t or time because that is the RTF for part B. Now, there's no standard rule when you want to isolate a certain variable. But let's say, for example, I want to isolate time. And of course, I want to remove the extraneous variables around it. My technique is to get rid of that denominator if there's any. First thing, because it makes everything else easier. So what I will do is I will multiply both sides by 2. So this can be cancelled. And you're going to have 2 dy on the left. And this is a t squared. Okay, and then let's divide both sides by a. So you're going to have 2 dy over a equals t squared. Okay, now you can see you still have the exponent 2. So for you to fully isolate time, you have to get the square root of both sides of the equation. And you're going to have, so you can now cancel that. And you're going to have square root of 2 dy over a equals 9. There you go. So that's the final equation. And all you need to do, you can actually flip that horizontally, meaning to say, you can put time on the left and then put this one on the right. They mean the same thing, okay? Because some people are used to seeing the RTF on the left side. So that's fine. But you can also stick to this one. It's also correct. So let's plug in the given variables. So we have 2 times negative 300 for the displacement divided by negative 9.8 meters per second squared. Okay, so it's going to give us 600 over 9.8. You get the square root of that. Okay, 7.82. So that's 7.82 seconds. So that's our final answer for part B. Okay, now the last step in problem solving that I would like you to consider is you have to evaluate your final answer. When I say evaluate your final answer, you have to look at the values that you can see and judge it if they are realistic. Let's say, for example, is this a reasonable speed given this height? For example, yes, of course, if every second the marble picks up 9.8 meters per second of speed, it's not surprising that it reaches this speed after a 300-meter descent, right? Okay, aside from that, how much time did it take for the marble to reach the ground? 7.82 seconds is also quite reasonable. It's not that fast, it's not that slow either, because 300 meter is actually pretty tall. But take note also that because the marble is accelerating continuously at 9.8 meters per second squared, it can easily get the ground really quick. Even if this is high, this is parang, it's like a skyscraper, I think. Okay, now in the next video, we're gonna do problem solving for case 2, but for this one, that's all for this video. At this point, I'd like you to answer the quiz items in part of the learning playlist, and then after that, submit the form and continue with the other tasks in the playlist, or submit the form and take a break. Have a great day.